Good morning, students. Good morning, students. In today's class, we are going to discuss about the derivation of equilibrium concentration of the Schottky defect in metal. Right. So here, in the previous class, we had a discussion regarding the equilibrium concentration of Schottky defect in ionic crystal. So, what is the basic difference? You'll find that there is a basic difference in the probability concept. So here, the same thing what we considered in the last class, since we don't know the exact procedure to evaluate the Schottky atoms which are present inside the metal. So the same thing what we have done in the previous class, we'll consider the ideal crystal. Let us consider the ideal crystal, right? And es energy, es is the energy involved, or instead of es which again you can also take ev, that is energy required to create the Schottky defect, right? N, capital N is the number of atoms, small n is the concentration of Schottky defect, right? So by using the probability concept, you already know that the probability concept, whenever you are not familiar with the thing that with the mathematical values or the mathematical function, you are not sure, then we'll use the probability concept. By using the probability concept, what we are doing, p is equal to what are the total number of atoms. You can just see we are writing in the numerator the total number of atoms, that is n factorial, and what is the remaining Schottky defective atoms, that is a small n, as you can just see the screen, where small n is the concentration of Schottky defective atoms. So n factorial into what is remaining here. See, very very important. What is the thing that is remain here? That is capital N minus small n. That is the remaining part. So the change in the entropy, you already know that entropy is nothing but it is the disorderness which is caused in the system. So since you are considering an ideal crystal, so what we are doing, we are applying some amount of heat, right? You are applying some amount of heat, or you are applying some amount of pressure to the ideal crystal. Then definitely the concentration of the atoms will be changing. The behavior of the atoms will change, and that behavior which is causing a change in the system, or in the, which, when I say a system, you can just refer that system as nothing but a crystal. The change in the concentration of the atoms which are residing in the crystal, that particular change is known as entropy. So how you are writing mathematically the entropy formulae, that can be given as S is equal to G. Entropy is denoted by S. So entropy S is equal to K as Boltzmann constant and logarithmic value of P. So log of P. So S is equal to K log P. So I think that uh, in the previous class also, if you have any doubt also in this class, we just definitely I will try to clarify that. So in the same manner, so in the previous class, there is a square here, right? Whole square. Now that is a case for ionic crystal. Equal number of cation ions are meeting. In the metals, you'll find that more number of cations will be there. So definitely, what we'll say that S is equal to, instead of that square, so we just don't write square here. So we just write P is equal to capital N factorial by small n factorial into capital N minus small n factorial. So the change in the entropy is given by S is equal to K log P, right? So the next one, see, K log P, log of P. P is what? You already know, N factorial by small n factorial into capital N minus small n factorial. See, I'm repeating. See, we have just started with the unknown thing, right? Let us consider a ideal crystal. So let us consider the energy required for the Schottky defect. Schottky defect is nothing but we can just, you can represent it with ES, or you can represent it with it can be represented with EV also. So N is the total number of atoms, small n is the concentration of the Schottky defective atoms. So that actually we are, see, our, what is our aim is that we are actually finding out the concentration of Schottky defective atoms. So what we are doing here is that we are using the probability concept, that is p is equal to capital N factorial by small n factorial into capital N minus small n factorial. So right, we just had a very good revision, right, of these steps. So the change in the entropy is given by S is equal to k log p, and you already know the p value is S is equal to k log capital N factorial by small n factorial, right, into capital N minus small n factorial, right. So with this, what you can write here, so the same aspect will be there. So n capital N factorial by small n factorial. So this is in the form of log of a by b. Just in the previous case also we had just written here. See, this is in the form of what? You can just see this here. We are taking the log of, right, log of a by b, right. So here b in the sense this whole part. See, I'm talking about this whole part. This is your b, right. So if you have think that you can easily understand this, this is exactly, this is your entire b, right. So this part is your entire b. So a is your this one, this is a here, this is a, right. So I didn't think you will have any problem with this. So you already know log a by b can also be written as log of a minus log of u. This I think that you have a very clear idea. This is very small, what you can say, the basic formula of the logarithm. Log a by b can be written as log a minus log b. So log a, see, log a is what here? Log n factorial. B is this entire thing. See, B means entire thing. Minus log n factorial minus log of capital N minus small n factorial. So with this, I think that you got a very clear idea. See how to solve this small mathematical equation, right? So this is what we have to do now. So I think that again, see, again, I'm repeating the same thing. Why? Because if you understand this particular one derivation very easily, so I think that yesterday's also you can easily understand. So what we have taken a ideal crystal. In that ideal crystal, we have taken energy. You can just see the energy required to create the Schottky defect. So here, where we have taken yes, you can just make it as EV also here. So capital N is the number of atoms, and small n is the concentration of Schottky defective atoms. So by using the probability concept, we can just write P is equal to n factorial by small n factorial into capital N minus small n factorial, right? So the change in the entropy which is caused in the crystal is given by mathematical formula S is equal to k log p. So S is equal to k log of p is what? N factorial by small n factorial capital N minus small n factorial. So here this is in the form of log a by b. So log a by b is nothing but this b is entire. I told you that this entire denominator value is here b. So that can be written as log a minus log of small n factorial minus log of n minus capital N minus small n factorial. So I already told you that since the factorial term is there, so we have to use a approximation, Stelling approximation. So we just go to the next slide wherein see in the next slide, when we go to the next slide, we can just see this applying the Stelling approximation, that is log x factorial is equal to x log x minus x, right? Clear, everybody? Applying the Stelling approximation, log x factorial is equal to s x log x minus x. So I already told you that when you just simplify this log x factorial, so you'll get x log x minus x. So this x is the variable. It may be any other variable, right? So for our case, you can just write s is equal to k log of n. So how I got this? So you see again, we can just have this. See, the previous case we had, see, log of capital N factorial. I already told you in the previous class also we have seen this. So again, I'm repeating this, the same aspect. Why? Because if you have not understood, it will vary. This can also be written as log n log n log n minus n. You can just see where I have just expanded the log n factorial and it comes to be n log n minus n. Clear, everybody? The next important aspect here that you need to understand is log, log small n factorial. This, if we expand this one, so n log, same aspect here, only the small letter and the big letter is changing here, log n, right? And this is what we'll write here, minus small n, right? The next aspect here is what? Log of, see again, it should, I think that with this you can easily understand the factorial expansion by using the Stirling approximation. So how am I expanding it? By using this Stirling approximation, this tells us that log x factorial can be written as x log x minus x. Here x is what? Same thing you have to write. X is what? Capital N minus small n log of into log of right, capital N minus small n. Clear, everybody? Right? Minus of capital N minus small n. This is actual expansion. So you can just see this. N capital N minus small n log of capital N minus small n. See, this is minus of capital N. So this will become positive. You can just see the previous slide also. When I just substitute that in the previous slide, so the values which are there in the previous slide, so it comes to be in this particular fashion. You just expand it, you'll get this particular aspect here. So with this, I think that you got a very clear idea how to do this. Say here plus n and here minus n get cancelled, here plus small n and minus small n. What is remaining? I'm written here s is equal to k n log n minus n log n as it is, minus of capital N minus small n log of capital N minus small n. So you can just see that which terms have been cancelled, and these terms which when they are cancelled, see this is the cancel, so you'll get this particular value. This is the term. So you just expand this. See, I have just expanded here. I've shown you that the log x factorial. So instead of x, what I've written here, capital A. So what will get? Log n factorial is equal to n log n minus n. And here log n small n factorial, which is given as n log n minus small n. So here log of capital N minus small n factorial, which is given as capital N minus small n log of capital N minus small n, minus of capital N minus small n. So you see, this is expansion what I've done. Remaining the sign, see, you can just see that there is a negative sign for before the minus log n small n factorial, and also minus of log of capital N minus small n factorial. So when you expand it, it comes to be in this particular value. And here, when you just write it down, this minus capital N and plus capital N will get cancelled, and plus small n and minus small n will get cancelled. So you'll get this type of values, right? So with this, I think that you understood, right? You understood this step, right? With this assumption, I'll move to the next one. So now, by using the law of thermodynamics, the change in the free energy function is given by F is equal to U minus Ts. You already know. See, whenever you are applying some amount of force to it, there will be definitely change in the energy of the crystal. So you are applying some amount of force here. So F is equal to, that is called free energy function, F is equal to U minus Ts, where U is the internal energy, and from that internal energy of the crystal, you are removing some, right? So the mathematically, when you remove some particular value, so that comes to be T into S, that is absolute temperature, and S is the entropy, right? So that can be written as, see, U already I told you that U is nothing but N into S. You can just see For your reference, you can just make this ES as EV also, right? So this is to make the variation for ionic crystal and also for the uh, metals, right? There should be some variation. So instead of this, you see what I'm trying to tell here is that here you can write this as V. See, this can be written as V. So n into EV, U in into EV minus KT log of n minus n log of C, as it is I've written capital N log n, capital N log n minus small n log n, as it is capital N minus small n log of capital N minus small n. So only the thing that is changing here is the function. This function is changed. F is equal to U is n into EV minus T. S as, see, S we got this the entire value of S. So we just substituted that S value here. So we got this right. So this with this what you can say that right. And I think that you got a very clear idea regarding this. So at equilibrium, the change in the free energy is minimum. So definitely at some constant condition, that is, we say that is equilibrium, the change in the free energy will be minimum. So how, see, this is the statement I'm telling you. So when you just go for any statement, theoretical statement, that should be verified in physics, that should be verified mathematically also. See, if I say that the equilibrium, at equilibrium, the change in the free energy is minimum. So what is that indicates mathematically? So that is the reason that the next step comes into picture, that is dou F by dou N, which is equal to 0, right? So dou F, so differentiating this free energy function with respect to the change which is occurred in the Schottky atoms, right? So the dou F by dou N, definitely it will be minimum. This is called the uh, equivalent, mathematical equivalent of this statement. The change in free energy is minimum can be mathematically written by a term called dou F by dou N is equal to 0. So right now, what is that? So dou F by dou N, you can just say dou F by dou N, that is 1. So I have written here, yes, right. See, I already told you this can also be written as this value is actually EV, right? For, see, this is for metal, so that is only the difference what we are showing, right? So here see here, n into ev as it is with respect to n, dou f with respect to c, dou f by dou n is equal to 0. So here left hand side you will get a 0, n into ev is there. So dou f by dou n means this value will be 1, and ev as it is I have written minus kt n. See, we are not differentiating capital N here. So this particular thing is very different. So this will become 0. So we are differentiating f with respect to small n. So wherever you find the small n value, so there definitely you have to differentiate. And the other terms will be 0. So there is a constant term, and the constant term comes to be the differentiation of the constant comes to be 0. You already know in the differentiation, right? So here we are going for this n into log n. So I think that n into log n. So what is the rule that we are taking here? N into, see, this is actually your u, and this is your v. So what we are doing, dou f by dou n. So d in means differentiation of u. First we are taking u, and then differentiation of u into v. So that is equal to, you already know, see, u v dash plus v u dash. So u is n. So I have written n here. V dash means log x, differentiation is 1 by x. Here x is not there. So what you'll write? N is there. So 1 by n. Understood? So minus, see, this is right, n into, so u v dash plus v into u dash. So minus is already there at the starting end. So minus into plus, definitely it will be minus. So v, see, v as it is here written. V you already know log n. So I've written log n. Then u dash is n. So dou f by dou n is what? Here dou f by dou n means this n with respect to n will become 1. So with the differentiation of it, log n into 1. So we are what we are writing, log n. Clear everybody? Now, see clear? This is actually V. This should be V. Remember, this is what here. We are just varying, right? For variation purpose, we are writing. Instead of that, you can write yes also. But it should, when we talk about metal and ionic crystal, there should be some difference, right? So that is the reason that I am making it to V here, right? So I think that see, this part is over. See, this part is over. Now what is the next one? You can just see. So we have differentiated n log n, and we got this particular term. See, we got this particular term, right, until this. This is the differentiation of n log n, right? We got the differentiation of n log n. Now we are going for the differentiation of, this is what we are taking it as u. This is u value. This is u, and this is v. So again, the same aspect here, d u into v, differentiation of u into v. So what it comes to at last, u v dash plus v u dash. Clear everybody? So u is capital N minus small n. So I've written, see, capital N minus small n is your u. So this expansion v dash means log x. So instead of x, what is there? Capital N minus small n. So log x is what differentiation? 1 by x. So x means capital N minus small n. Again, you have to differentiate. So when you differentiate with respect to n, so what it will minus n means what it will be? Minus 1. Clear? This part is over. See, the first term is over, right? This is your first term. This is the first part that we have done. Clear everybody? Clear? So here the uv dash we have done. See, n capital N minus small n into 1 by capital N minus small n, again differentiation, minus 1. So uv dash is over. The next one is plus v into u dash. Already minus is there, minus into plus, you'll get minus here. V, what is v? You already know. What is v here? Log of capital N minus small n. So I have written here log of capital N minus small n. So u dash means capital N minus small n. When you differentiate, yeah, we have already differentiated in the first step, right? U n minus capital N minus small n is again differentiated, and you'll get the value as minus 1. So you have written here minus 1. Clear, clear, very clear, right? You write this as v. This is v for our comfortableness. So here, what you can do is that you can just cancel it, right? Numerator is small n, denominator small n. Numerator capital N minus small n, denominator capital N minus small n. Anything else that can be cancelled out? No, nothing. So what is remaining here? Minus 1, minus log n, right? So here minus into minus plus, plus 1. Clear? Minus of log n, minus into minus plus n. So you can just see the next one. See here, what it comes to here? V. Right. Now what will come into picture? See, ES minus, so ES minus KT log of, see, ES, right? ES means what I already told you, right? When you talk about this, right? Okay. Now, see here, ES minus KT. See, ES minus KT, this term will be there, right? ES minus, ES is EV here. We are just considering ES, you can just make it at EV also, minus KT. right? Es minus kt. So what is come? Minus 1 is already there. Minus 1 is already there. Minus log n plus 1 plus log of capital N minus small n. So this minus 1, see, you can just make this minus 1 will get cancelled here. See, just a minute. This will get cancelled. This minus 1 and plus 1 get cancelled. Here you can see. See, minus 1 and plus 1 will get cancelled. So what will be remaining here? EV or ES minus KT minus of log n plus log of capital N minus. You can just see this. ES is equal to KT minus log n and log of this term. So log of capital N minus small n. So ES by this will go to the left hand side. So what it will be when it go to the left hand side? ES by KT is equal to minus log n plus log of capital N minus small n. So this is what we got. See, this is in the again, this is in the form of log A minus log B. So what you can do here? So previously, see, this is what we got. So here ES by KT minus log n plus log of capital N minus n. This we got, right? So this is in the form of log A minus log B, which is equal to ES by KT. So what will be remaining here? ES by KT is equal to log of capital N minus small n. So log A minus log B can be written as log A by B. So ES by KT is equal to log of capital N minus small n by small n. So this is the value you got, and from here what you can do is that see what I am doing here, log A minus log B have done. Okay, here log A minus log B. So this log, when you go to the left hand side, what it will become? And here what I told you, this is your EV, right? You can just make a note of it, that wherever you find, yes, right, you'll write it as EV. So this is what we got. So EV. So log, when it is go to the left hand side, it will become now. See, this will become. See, exponential of ES by KT is equal to capital N minus small n by small. So log, when go to the left hand side, will become exponential. This term will come in the exponent form, e to the power of EX by KT, which is equal to capital N minus small n by small n. Right. So now you already know in the previous derivation also, the same derivation we are going for, e exponential of ES by KT is equal to capital N minus small n by capital N. When n is very small, and small n is very small than capital N, so n can be neglected. So what we do here, so before this, we just what we done in the previous one, we want to do the same thing here. So since capital N is very much greater than small n, so what the value of capital N minus small n will approximate it to capital N also. So right, how we are writing this? I already told you that if n is very much greater than n, so what we are doing here is that capital N, right, minus small n can be approximated to capital N. So this factor will now become capital N. So capital N. So instead of this, what you can write? Capital N by small n. So and we want actually this value. See, what is our aim? Equilibrium concentration of Schottky defect in metals. So we want this small n value here. So how I can get the small n value? See, small n, now the next step will be like this, right? Small n is equal to e to the power of, right, when it go to this when it go to this side, e to the capital E, yes, so s nothing but here EV, you can write EV here by KT, right? And this is what E n is equal to, so So this is just a minute. Where is this? When n is going there, see, n is going there. See, n is going there. So what it will be? Right. I don't say it is going in this particular aspect. So n is going there. So we want the n value. So instead of that, this will go to the this side and it will become negative. So n is equal to. So n will become small n will be capital N minus small n is equal to capital N e to the power of minus es by kt. So with this, you can just say that in the previous case also, what we have done in the previous case and this case is very much similar. So here, uh, see, in the previous case also we got this value. So n small n is equal to capital N e to the power of minus es by kt. In this case and the previous derivation, only difference you find that 2, right? 2 is there in the denominator. That is the case for the ionic crystal, and this is the case for the what you can say metal, right? So with this, I think that we have gone for the completion of the second derivation. So if you have any problem with this derivation, you please try to do this derivation as many times as possible, such that you will have very clear idea. And if you know some very simple formulas, you can easily do this and you can just reproduce the same thing in the examination also. With this, we just conclude our talk today's class. Thank you everyone. We'll meet in the next class. Thank you.